Welcome to Module 6, Lecture 5. This lecture is on coherent states, and it's subtitled Moving and Pushing the Ground State. The idea about coherent states actually starts with Schrödinger in 1926. Schrödinger was the first person to discover the coherent states, and he looked at them when he was interested in looking at the classical limit of the quantum solutions to the simple harmonic oscillator. These states can be thought of as the analog of pulling the mass on a spring, as you would in a classical mechanics situation. However, we're going to allow ourselves to not only just extend the mass of the spring, but also give it a push when we release it. And that's what a coherent state is. We're going to show this analogy next. And in addition, we're going to develop this analogy to discover what these states are, what they mean, and how we work with them. Later in the class, we're going to discuss squeezed states, which are even more bizarre than the coherent states. So first, let's remind ourselves about how we describe translation with respect to position and momentum. So we worked out previously two operators that involve the translation of position and momentum. We use these to calculate wave functions by translating the origin in position space or in momentum space and using an operator to represent that translation, and then working with the operator to calculate the wave functions themselves. So let me remind you what those translations are. On the left, we have the translation in position, and it will translate by an amount of x sub 0. And on the right, we have the translation with respect to momentum, and that will translate the momentum by amount of p sub 0. You notice the signs and the exponents are different. That's the way that it comes out because of the commutation relation between position and momentum. Now, suppose we want to apply both of these operators, one after the other, onto the ground state. We can use the BCH identity to put both operators into the exponent. In this case, it would be viewed as an entangling identity. And we can use the Weyl form because the commutator of x with p is IH bar. And if you carefully work out the correction term up to a sign, it's very easy to work out that it's going to be e to the I over 2h bar x0 times p0, because I have to multiply the coefficients of the x with the p times each other. I have to divide by 2. And then I have to take the commutator of x with p, which is IH bar. And then I just have to worry about getting the sign right, depending upon which order I was starting from, whether I did the momentum translation first or the position translation first. But in any case, this correction factor is just a complex phase. It's a global phase. And as we recall, quantum mechanical states are undefined relative to a global phase. So I can always add any global phase that I want, and so we can just ignore that global phase. We can get rid of it and not worry about it, and instead of thinking of applying one translation after another, we can think of applying both of them together if we want, and then we don't worry at all about the phase factor. So when we extend a spring with corresponding to the ground state and give it a push, it corresponds to this operator, e to the I over h bar p0 x hat minus I over h bar x0 p hat, acting on the ground state. All right, we'd rather work with the ladder operators, the raising and lowering operators. So it's easy to make the conversion. On the right-hand side, you see a table that shows you how the position and momentum operators are related to the raising and lowering operators in the Dirac notation. So we just substitute in for the x and for the p. It's a relatively straightforward transformation. We're dividing by an h bar and multiplying by a plus or minus I. Now what we're going to do is we're going to collect all of the coefficients of the lowering operator and of the raising operator. We're going to define this coefficient alpha, which is equal to x0 square root of m omega over 2 h bar plus I p0, 1 over the square root of 2 m omega h bar. And using that defined number, it's a complex number, we can rewrite the operator in the form of the exponential of minus alpha star a plus alpha a dagger. And we call that operator d hat of alpha. That operator has a name. It's called the displacement operator. Displacement indicating that we're displacing both position and momentum. And what we say is that when we displace the ground state using this displacement operator with this parameter alpha, which corresponds to a particular displacement of position and momentum, then we call that state alpha. It's called the coherent state, and the parameter that the coherent state is labeled by is this parameter alpha, which summarizes the shift in position and momentum, and that's the displaced ground state in position and momentum. Okay, the claim, and this is a very surprising claim, is that this coherent state is an eigenstate of the lowering operator with an eigenvalue given by alpha. Turns out the proof is really not that hard, so let's go ahead and prove it. We simply have to use the Hadamard identity. So let's start with our definition of the A operator acting on the state alpha. I put in what the alpha state is by writing out that displacement operator explicitly. And now I'm going to use the multiply by 1 trick on the left of the A operator. And now I'm going to recognize that I have a Hadamard. I'm going to evaluate that Hadamard. And you see now we're in a really good situation because the A operator, when it acts on the ground state, it annihilates the ground state. So that A operator is going to disappear, and I'm left with a number times the ground state. Of course, I can move that number out to the left-hand side, and then I just recognize the definition of the coherent state, and we recognize that the coherent state is indeed an eigenstate of the lowering operator, and the eigenvalue is equal to alpha. Now, you might be a little bit stymied at this moment because alpha is a complex number. And all of the eigenvalues we've been dealing with before have just been real numbers. That's because we were working with Hermitian operators. This is not a Hermitian operator, and non-Hermitian operators can have complex eigenvalues. But non-Hermitian operators, the eigenstates, do not form a complete set, and so we won't be using that property. But the fact that the lowering operator has a complex eigenvalue, that's perfectly allowed within the theory because it's not a Hermitian operator. Okay, this is really a godsend for us because it means any matrix element that we want to evaluate between any two coherent states can immediately be evaluated if we write the operator in the normal ordered form in terms of the ladder operators. We just replace the operators by the corresponding coherent state eigenvalues. So when the lowering operator acts to the right on the state alpha, I just pull out the number alpha. And if I take the Hermitian conjugate of that relation, you can immediately see that when the raising operator acts to the left onto a state beta, a bra beta, it will pull out the number beta star. It's a star because to get that equation, I had to take the transpose conjugate or Hermitian conjugate of the eigenvalue equation for the lowering operator when it acts on a ket. And when I do that, I get a complex conjugate of the eigenvalue. Okay, we're going to be using this later in the lecture to evaluate uncertainty. Now, the coherent state is not an eigenstate of a dagger. And let's just go through the reasoning why that occurs. So we can start the same way with an operation of a dagger onto the coherent state, and we put out the definition of what the coherent state is. We multiply by 1 again. We recognize we have a Hadamard. We evaluate the Hadamard. And we get this form A dagger minus alpha. Of course, the minus alpha I can pull out. But A dagger acting on that state, that doesn't annihilate that state. It's just another state. And so I get some other vector that's in some other direction. It is not an eigenvalue-eigenvector relationship. And so it is not an eigenstate of the raising operator. Now you might ask, why in the world is it an eigenstate of the lowering operator? Well, it turns out it just comes about from the fact that we shifted the position and momentum. And I want to illustrate that for you now. So let's consider a Hamiltonian that has shifted the momentum by p0 and the position by x0. We simply write it as the operator p hat minus p0 squared divided by 2m plus 1/2 m omega squared, the operator x minus x0 quantity squared. That has then shifted my position and momentum in the Hamiltonian itself. Let's work this out using our factorization technique. You can rewrite this Hamiltonian in terms of a raising and lowering operator that is defined in this fashion, with an x hat minus x0 and a p hat minus p0. and you get it in the form of h bar omega a hat prime dagger a hat prime plus a half. I really recommend you pause the video, write down the 3 lines of algebra that it takes to put it into this form, and verify that you really get it in this form. Okay, now our factorization method tells us that the ground state is determined by a subsidiary condition, and here that subsidiary condition is modified to be a hat prime acting on 0 prime equals 0. Now all we do is we simply recognize that that a hat prime has an a hat in it. If I look just at the operator terms in the definition of a hat prime, that's actually a hat. So I can write a hat prime as a hat minus alpha. So a hat prime equals a hat minus alpha. And so when I plug that into the subsidiary condition, we immediately find that it tells us that a hat acting on 0 prime is equal to alpha acting on 0 prime. But we know what state does that. That's the coherent state alpha. And so whenever we work with a shifted Hamiltonian and we look at the shifted ground state, it becomes an eigenstate of the original lowering operator with an eigenvalue given by alpha. And so that's the reason why the coherent state is an eigenstate of A. The eigenvalue-eigenvector relationship simply comes from the shift of position and momentum. Okay, we're going to now write the coherent states in terms of the energy eigenstates that we label with the integer n. To do that, we're going to use the BCH identity, and we're going to pull out the lowering operator on the right. So I've written it out explicitly for you. That displacement operator becomes e to the alpha a hat dagger e to the minus alpha star a hat minus 1/2 modulus of alpha squared times the commutator of a with a dagger. You might be a little bit confused about why there's a minus 1/2 there as opposed to a plus 1/2. That's because I've moved this commutator term to the other side of the equation. When we derive the BCH, we put that term on the term where we had the sum of the exponents. But now we're moving it on to the other side because we're putting it on the side that was the e to the a, e to the b term in the BCH representation. And that's perfectly fine to do, especially since in this case it turns out to be a number. So now we just evaluate that commutator. It's equal to 1. And now I'm going to move that number to the left-hand side. And now remember, a hat annihilates that ground state. So if I expand that exponential in a power series, only the first term, the 1, survives. All the terms that have powers of a hat, they all give 0 when they act on the ground state. So I can get rid of that term. And now what I'm going to do is I'm going to write the power series out for the exponential term in terms of the raising operator. And now I'm going to recognize that if I borrow a 1 over square root of n factorial times that a dagger raised to the nth power, I get the nth energy eigenstate. So I can replace that by the nth energy eigenstate. And now we have our representation of the coherent state in terms of the energy eigenstates. It's an infinite sum, but this form is actually very useful for doing a number of different kinds of calculations. For example, what we can do is we can use this to also verify this eigenvalue-eigenvector relation. We have to remember what happens when we operate a ladder operator onto an energy eigenstate. It gives us a square root of n times n minus 1. It lowers the index by 1 and it multiplies by the number square root of n. So if I look at operating the lowering operator onto this coherent state and I'm working in this energy representation, I'm going to have that a hat acting on the nth energy eigenstate. I replace that by square root of n times n minus 1, and now I recognize that the square root of n can cancel one term in that n factorial, makes it n minus 1 factorial. I can factor, and also notice that here, when n equals 0, that term is equal to 0 because the a operator annihilates the ground state. And so that summation now I can replace by a sum going from n equals 1 to infinity. Now I also can pull out a factor of alpha from this and make it an alpha times alpha to the n minus 1. And now I simply shift n goes to n plus 1 in the summation. So I make it go from 0 to infinity. And you recognize here that we now have the coherent state. So I can replace the coherent state and I have verified the eigenvalue-eigenvector relationship. So we can do it this way as well. And it's very useful to see the multiple different ways in which you can work with these operators when you are working in quantum mechanics. Knowing how to solve a problem more than one way is often very useful and helpful for helping you understand how things work. So now you have seen two different ways in which we can verify that the coherent state is an eigenstate of the lowering operator. All right, we also can look at the normalization of the coherent state. So we're going to look at the overlap of two different coherent states. So we're going to look at beta overlapped with alpha. I just write them out in terms of these energy eigenstates. And so I have two summations. I have two of these Gaussian-like factors in terms of the alphas and the betas, and I have these infinite summations with the alpha and the beta star raised to a power divided by the square root of the corresponding factorial. And then I have the overlap of the mth energy eigenstate with the nth energy eigenstate. We know what that overlap is because energy eigenstates are orthogonal. So that's just equal to this Kronecker delta mn, which means I can set m equals n and get rid of one of the summations. And so I do that. And now look, this is an exponential. It's an exponential of beta star alpha. So I can replace that by the exponential, and we now have this nice, neat, compact formula for the overlap of two coherent states. Let's go ahead and set alpha equals beta. Then you can see that because alpha star times alpha is mod alpha squared, and mod beta squared becomes mod alpha squared in that limit, the normalization is equal to 1. So these coherent states are normalized. But you might be surprised to learn that if beta doesn't equal alpha, this inner product or this overlap is not 0. The coherent states with different parameters are not orthogonal. But the overlap does get smaller and smaller the farther apart the real part of the alpha is from the beta. You can, for example, take a look at choosing beta equals minus alpha, and you can very quickly see that that expectation value, that overlap, gets very small as alpha gets larger and larger. You're going to have a homework problem where you verify what is called the completeness relation for the coherent states. They form what is called an overcomplete basis, and you'll be able to investigate that in a problem in the homework. All right, we're on to our last topic for this lecture, uncertainty. We simply want to calculate the uncertainty for both position and momentum in these states. Remember the uncertainty, the square of the uncertainty in position in the coherent state alpha is given by the expectation value of x squared minus the expectation value of x quantity squared. What we're going to do is we're going to substitute in for the x and the p in terms of the raising and lowering operators, because whenever you work with coherent states, you want to express your operator in terms of the ladder operators, because we know how to evaluate ladder operators acting on the coherent states because of this eigenvalue relationship. So we're going to go ahead and substitute that in. And when we do that, we get a number of different terms that are going to come out. So first, using our table, our little formula on the right, we can just substitute directly in. And now we have to expand those terms. And so when we expand the terms, remembering that operators, the ordering matters, we get an a hat squared, an a hat a dagger, an a hat dagger a hat, and an a hat dagger squared in the first term. The second term is just an a hat plus a hat dagger. I don't have to worry about any ordering there. Now, all of those terms in the left-hand term are in normal ordered form except for the one in red. So how do I get in a normal ordered form? I just do the add 0 trick. That gives me a commutator. I can rewrite it as a dagger a plus the commutator of a with a dagger. Commutator of a with a dagger is 1. And so when I substitute that in, I get 2 a hat dagger a plus 1. Now it is in normal ordered form. We can immediately evaluate it. The way that we do this is every a operator gets replaced by an alpha, and every a hat dagger operator gets replaced by an alpha star. Even in the term on the right-hand side, which you might be confused by, that a hat operator I evaluate to the right, it gives me alpha. The a hat dagger term I operate to the left, it gives me alpha star. Okay? So when we plug that in, we get alpha squared plus 2 mod alpha squared plus 1 plus alpha star squared minus the quantity alpha plus alpha star squared. Okay, now when I square that, you see I'm going to get an alpha squared plus 2 mod alpha squared plus alpha star squared. that cancels every term except for the 1. And so I get h bar over 2m omega, and it's independent of alpha. So that's an important thing to remember. Now we're going to look at the fluctuations in momentum, and we're going to do the same thing. We're going to represent it in terms of position and momentum. I have put up for you again the table to remind you about what we're substituting in. So I'm substituting that p hat operator in, and it's squaring. The one thing to remember is the p hat operator has a 1 over I. So when I square that, I'm going to get a -1 in the expression. And now we do the same thing. We expand that quadratic, taking into account the operator ordering. We look at the normal ordered form. Every term except that red one is already in normal ordered form, so there's only one term I have to modify. I use the add 0 trick and evaluate the commutator and find that it's -2 a dagger a -1. And now I just evaluate by replacing those operators with the alpha star and the alpha respectively. And again, you can see when I do the square of the term on the right, I do the square of the term on the right, it's going to cancel every term except that -1 term. There's a -1 in front, so the net effect is we get h bar m omega over 2. And again, it is independent of alpha. Okay? Now we can look at the uncertainty product. Of course, it's going to be independent of alpha because both terms were independent of alpha, but it's also equal to the value that it had in the ground state, which of course it must be because I can set alpha equals 0 and I look at, and the coherent state is just looking at the ground state. So the uncertainty relation is the same for the ground state, meaning the shape of the wave function stays exactly the same when I displace it, which, you know, of course is what happens because I simply displaced the ground state. I didn't do anything to it. I didn't change its shape. I simply displaced it. Okay? So this is just summarizing what I said before. Because we just did this shift of position and momentum, it's very reasonable that the uncertainty is unchanged because the shape of the wave function that I'm working with is unchanged as well. We're going to discuss how these coherent states evolve as a function of time when we discuss time evolution. That's not going to be for maybe a month and a half, maybe 2 months, but we're going to be discussing that toward the end of the class, and we're going to use the coherent states as one of the examples. And the time evolution of the coherent states is actually very interesting, and it's easy for us to solve for it. So we're going to be doing that later in the course. And that brings us to the end of lecture 5 of module 6.